Now, let us detail the idea behind the backpropagation algorithm. First, recall that our aim using backpropagation is to compute the gradient of the loss. Then, we can use a gradient-based optimization algorithm in order to update the parameters of the network. So, backpropagation is not an optimization algorithm. Backpropagation aims at computing the gradient of the loss based on a batch of data. To keep things simple here, we consider a batch of data composed of just one observation, the ith observation. So the gradient we want to compute is the gradient of Li theta, where theta stands for all parameters of the network, both weights and biases. So this quantity, this gradient, is a large vector whose size p equals the number of trainable parameters in the network. Each component is, by definition, the partial derivative of the loss with respect to a parameter of the network. Considering an arbitrary ordering of the parameters from 1 to p, we can write the gradient of Li as such. To compute the gradient, we need to compute each component of this vector. For example, one component corresponds to the partial derivative of the loss with respect to this weight in this connection. Indeed, recall that each line here corresponds to a weight and the biases are not depicted here, one per neuron. So let's say we want to compute the derivative of the loss being accessible at the end of the network with respect to the parameter in our range. So the loss depends on the output unit at the end of the network. The output unit depends on all neurons of the previous layer that are connected to it, that is this one, and all connections in blue. So the loss depends on all connections between the third hidden layer and the output unit. Then the output of this neuron, which has an impact on the loss, depends again on all connections parameters that are connected to it, that is this one, and so on. Now recall that we want to compute the partial derivative of the loss with respect to the parameter in our range. Now let's take this neuron for example. Since there is no connection between this neuron and the parameter in our range, you see that the output of this neuron is independent of the parameter in our range. So this connection won't appear in the computation of the gradient of the loss with respect to the parameter in our range. So we can remove it. It is the same for this neuron and all neurons but this one. Here we have just considered the first neuron in the third hidden layer. If we consider the second neuron in the third hidden layer, this one, you see with the same reasoning that the only connection that will matter in the gradient computation is this one. Because all other connections between the second and third hidden layer are not influenced by the parameter in our range. All in all, the connections that matter in the gradient computation are now depicted in blue. So, to summarize, the loss depends on the output layer depends on all neurons in the third hidden layer, the third hidden layer depends on this neuron in the second hidden layer, which is the only neuron in the second hidden layer to be influenced by the parameter in our range. We will see in a moment the precise equations used to compute the partial derivative of the loss. For now, a general comment. We have considered the parameter in our range, but we could have considered another parameter, let's say this one in red. For this new parameter, you can apply the same reasoning, pinpoint all connections that link the loss to this parameter, and compute the partial derivative. In fact, you can do that for any parameter in the network. Since there is a large number of connections involved in each computation and a large number of parameters, it would be very costly, computationally speaking, to apply the reasoning for each parameter of the network independently. Instead, we are going to use the backpropagation algorithm. To describe the backpropagation algorithm, let me introduce some notations. We call Z the input, the linear combination of a generic neuron, and Z1I the input, again the linear combination, of the ith neuron in the first hidden layer. For example, the input of this neuron, which is the second neuron in the first hidden layer, is Z12. We adopt the same notation for the other layers. To simplify notation a bit, we're going to denote by C theta the loss function, which can be computed on one observation or on a batch of observations of any size. The fundamental remark underlying the backpropagation algorithm is noticing that it is easy to compute recursively the partial derivative of C with respect to any zji. In turn, if you have access to this quantity for all neurons in the network, you can easily compute the partial derivative of C with respect to any parameters of the network. To see that, consider this weight. We want to compute the partial derivative of the loss C with respect to this weight that we call W. Since the loss C depends on all z2i, according to the chain rule, the first derivative is equal to the sum over all neurons j in the second hidden layer of the partial derivative of C with respect to z2i times the partial derivative of z2i with respect to W. As noticed before, only z21 depends on W. Therefore, all terms are null except the one corresponding to z21, which leads to this formula. We mentioned that the first partial derivative can be computed recursively. The second one is easy to compute directly since it is nothing but the derivative of a linear combination with respect to one parameter of this linear combination. The same reasoning holds for computing the partial derivative with respect to any bias. To conclude the presentation of backpropagation, we just need to explain why the partial derivative of C with respect to zji can be computed recursively. To see that, let us consider this neuron Z24. And we try to compute the derivative of C with respect to the quantity, assuming that we have access to the derivative of C with respect to the 3i for any I. Since C depends on the neurons of the third layer, and in turn these neurons depend on Z24, one can use the chain rule again to derive this expression. We were able to compute the partial derivative of C with respect to Z3i. Besides, the second term is easy to compute since there is only one activation function and one linear combination to obtain Z3i based on Z24. Then we are able to compute the partial derivative of C, and we have done it recursively. The overall strategy of backpropagation works as follows. You start by computing the gradient of the loss with respect to the input of the last layer. This corresponds to the partial derivative of C with respect to Z41. Then, using the previous reasoning, you can compute all partial derivatives of C with respect to any input of the third hidden layer. You can then compute the partial derivative of C with respect to any input of the second hidden layer, and so on. Once you have all these quantities, you can use them to compute the quantities of interest, the partial derivative of C, with respect to the weights and biases of the network. Note that it is quite different from choosing a weight in the network and compute the gradient, since with backpropagation, you just need one path, called backward path, in the network to compute all quantities. Since you start at the end of the network and go back at the beginning to compute all quantities, this algorithm is naturally called backpropagation. We often say by abuse of language that we backpropagate the gradient through the network.